In this video, we'll be looking into the introduction part of transfer and conquer approach. So transfer and conquer is a general algorithmic design technique which involves modifying a problem instance to make it easier to solve. So a particular problem, if you are given a particular problem, you try to transfer it. So the problem instances could be one thing is it could be simplified, that is simpler instance, or some other representation of the input so that solving the problem becomes easier, or choosing a reducing the problem or choosing a different problem instance could be another approach. So these three are the variations of transfer and conquer approach. So this is so there are basically two steps. One is to transfer and the other one is to conquer the result. So this was about transfer and conquer approach. Let's move on to balanced search trees. So under balanced search trees, we have binary search tree. So binary search tree is a binary tree whose nodes contain elements of set of orderable items. One element per node, yes, so that all elements in the left subtree are smaller than the elements in the subtree's root. So if you consider this part, on the left hand side, a root is 20 here. On the left hand side, we have 10 because 10 is lesser than 20, so left hand side it will be there. And on the right hand side, greater than the root node, what do we have here? 30. And if you check to this, the main root node here, left side we have 20 which is less than 40, and right side we have 50 which is greater than 40. So that is what that is how a binary search tree is designed. Okay, so there could be situations where unbalanced binary search tree is transformed into balanced one. So because of this, such trees are called self-balancing trees. So in order to achieve this, we'll be making use of several approaches, that is AVL tree or 2-3 tree and so on. So if you consider this binary tree, in this, to search element 30, so if I have to search element 30, I'll start from the root node. From root node, compare 30 with the root node. 30 is lesser than 40, right? So it will look into the left hand side. Now coming to left hand side, here we have 20. So 20 again will compare. 30 is greater than 20. So it will be right hand side of 20. So 1, 2, 3. There are 3 comparisons being made here. Coming to 60, firstly I'll compare it with 40. Yes, it is greater than 40. So I'll come to the right hand side. Next, I'll compare it with 50. Yes, it is greater than 50. 60 is greater than 50. So I'll come to the right hand side. And again, here I'll come and find the 60. 3 comparisons here also. Next, I have 32. So I'll compare each and every, I'll start from the root node and I'll keep on comparing till the leaf node. And if I don't find it anywhere, then it is not found. So we can say that this particular binary tree has 3 levels, right? The height is 3 here. So maximum number of comparisons depend on the height of tree. Yes. So height of binary tree can be minimum log n or maximum n. Maximum n condition we can apply it when the element is the element which we need is not present in the tree itself. Okay. So problem with BST is that height is not under control. So because depending on how the key elements are entered, its values are varying. Okay, so to achieve better efficiency, we need to minimize the height of search tree. So I'll explain this with an example. If I enter 10, 20, 30 as inputs, so I'll start with 10 and then I'll check 20. So for 20 is greater than 10, right? So it will come on right side. Again 20, again I have 30 here. 30 is greater than 20, so I can write 30 here. So I have got this particular tree here. Next, let me check if I give 20, 10, 30, how will it be? 20 here, 10 here and 30 here. So for this, the height was 3 and 1, 2, 3. For this, the height is 2. And if I write 30, 20 and 10, then it would be 30, 20 and 10 here. So again height is 30. So depending on the order in which the elements are entered, our height is varying here. So this is the problem with binary search tree. In order to achieve better efficiency, we need to minimize the height of such trees. Okay, so for that we'll be making use of AVL trees. So AVL tree is an efficient binary search tree in which balancing factor. So in AVL tree we'll be speaking of balancing factor of every node is used to analyze and reorder the binary search tree to get balanced binary search tree of minimum height. We have two aims here. One is to get the balanced search tree and with minimum height. So both could be achieved by using AVL tree. So it is a strictly balanced tree. That is, it has to be balanced completely. So the balancing factor, what is balancing factor? The balancing factor is the height of left subtree minus height of right subtree. So for a given binary tree to obey AVL tree condition, the balancing factor of every node present in the tree should be in the range -1 or 0 or 1. Okay, so next we have the rotations. Okay, we have these binary trees which are given here. Let's check if it is AVL tree or not. Starting from this 0. So is there any left subtree, right subtree to this? No. So I'll put 0 here. Here also 0. So one thing to remember, leaf nodes, in case of leaf nodes, balancing factor is always 0. So here 0, 0. Here also 0 I'll write. Now coming to 4 here. So left subtree I have one node here and right I don't have anything. 1 minus 0 is 1. And coming to this 5 here, I have two elements, two nodes here, two nodes here. 2 minus 2, 0. Coming to this part, I don't have anything on the left part, that is 0, and on the right part I have 1. So it will be -1 here. Now checking for 20 here. On the left hand side I have 20, but on the right hand side I don't. On the left hand side I have 1 node, and on the right hand side I don't have anything. So it will be 0 minus 1 minus 0. I'll get 1. Okay. Now I'll find the balancing factor for this node 10. So I have 1, 2, 3. 3 nodes are there here, and on this side I have 1 and 2. 2 nodes are there. 3 minus 1, 3 minus 2. Here 2 nodes, here 3 nodes. 3 minus 2 is 1. So I'll be left with 1. So if I check the balancing factor for each node present in this tree is 1 or 0 or -1. So I can say that this is AVL tree. Now let's check for this. For 0 it will be 0, for 8 it will be 0, for 20 it will be 0. 4. So 1 minus 0 is 1 here, and 7. 0 minus 1 is -1 here. 5. 2 minus 2 is 0 here, and here I have 1, 2, 3. 3 minus 1. 3 minus 1 is 2. But then 2 is not acceptable. Balancing factor should be either -1, 0 or 1. So I can say this is not a AVL tree. Next I'll check for this. So for 6 it will be 0, for 11 it will be 0, 3, 32, 0, 49, 0. Now checking for 10. Left side I have 1, right side 1 node is there. 1 minus 1, 0. 1 minus 1, 0. Coming to 30, the root node. I have two elements, 2 nodes here and 2 nodes here. 2 minus 2, 0. So this has 0 as its balancing factor. So I can say that this falls under AVL tree. So now a question might arise. Given a tree, given a binary tree, it is not AVL tree. In order to balance it out, unbalanced binary search tree to AVL tree, I need to perform rotation operation. So rotation operation is performed. There are two types of rotation operations. One is the single operation, one is the double operation. That is double rotation, single rotation. Single rotation, I have left rotation and right rotation. And coming to double rotation, I have left right rotation and right left rotation. These are the combinations of left and right, but then they are clubbed as one step itself. Okay. Now let's look into each rotations now. So firstly we have the right rotation. So if I check the balancing factor for 1, it is 0. For 2 it is 1 minus 0 is 1 here, and for 3 it is 2 minus 0 is 2. So this is not balanced, and there is unbalancing happening in the left hand side. So what will I do here? I'll perform right rotation here. So I'll rotate it this way. Okay, when I rotate it this way, 2 will go up and 3 will come down. So it will be of the form 2, 1 and 3. So if I write the balancing factors here, it will be 0, 0 and 0. So now this is balanced, right? Yeah, this was about right rotation. Whenever we see the unbalance happening at the left side, we perform right rotation. Okay, so here we have performed right rotation. Coming to left rotation, I can see that on the right hand side there is it is not balanced properly. So here I have 0, here I have -1, here I have -2. So in this case I need to perform left rotation here, L, here R. So when I perform left rotation, 2 will go up and 1 will come down. So it will be of the form 2 will go up, 1 will come down, and 3 would be here. Writing balancing factor for these, it will be 0, 0, 0. Yeah, done. Now coming to the LR rotation. So for 2 the balancing factor is 0. For 1 the balancing factor is -1 here, and for 3 the balancing factor is 2 minus 0 is 0. So I can see that one time we are going left and on the other side we are going right. So when we go from left to right, here there is unbalance happening in the binary search tree. So in order to overcome this, we'll have to perform left rotation once and right rotation once. Instead, we can directly, whenever there is LR or RL condition, no, so keeping one node as the middle node, the other two extreme nodes on above and below, like 3 and 2 here and 1 and 2 here. So you just swap these. Okay. So when you swap these, no, you can directly write the answer without performing two-step rotation. But then yeah, you need to show like left. Firstly, here will go right and here will go left. So both the operations need to happen and then we'll obtain the LR rotation part. But then directly if I write the value, so 2 will go up. Okay. So 2 will go up, 1 will come on this side and 3 will come on this side. So here if I write the balancing factor 0, 0, 0. Coming to RL rotation. So first I'll go this side and again I'll go this side. So for this also send 2 up. Now 1 here and 3 here. 0, 0, 0. This was about right rotation, left rotation, LR rotation and RL rotation. We'll understand this better when we solve problems on it. So let's look into the first problem. That is, we have here construct AVL tree for list 5, 6, 8, 3, 2, 4 and 7 by successive iterations. So let's start from the first step. Let's consider 5. Yes, I have written 5. So balancing factor of 5 is 0. So I can proceed further. Now I have 6. 6 is greater than 5. So it will come on the RHS right side. Okay. 5 followed by 6. Now let me write the balancing factor 0 here and here I have nothing. So 0 minus 1 is -1 here. Next, this is okay. Balancing factor it should be 1, 0 or -1. So they are the acceptable balancing factor is under -1, 0 and 1. So it's okay. I can proceed further. 8 I have. So 8 is greater than 5. Yes, on the right hand side it will go. 8 is greater than 6 also. So again it will go on RHS, right hand side. So let me write the balancing factor. For 8 it will be 0. For 6 it will be 0 minus 1, that is -1. And for 5 it will be -2. So I can see that on the right side I am the unbalance is happening here. In this condition I need to perform left rotation. Okay. I am rotating this side. Okay, sorry, I'm rotating this side, okay. So it will be, if we see the balancing factor for 8 is 0, 6 is -1 and 2 is -2. So I need to perform left rotation, shift 5 to this side and take 6 above. So it will be 6, 5 and 8 here. So for this, if I add the balancing factors 0, 0 and 0, done. I'm done with 8. Now I have 3 here. So 3 is less than 6, so it will come on the LHS side, and 3 is also less than 5, so it will again come on the LHS side. So I will write 3 here. Now if I write the balancing factor for this, it will be 0, here it will be 1 and here it will be 0. Yes, so for 6 it will be 2 minus 1 is 1, so it is again acceptable. Next I have 2 here, so I'll add 2 now. So let me write it again. 6, 5, 3. 2 is less than 3, no, so it will come here, and 8 I have here. So in this condition, 0 is the balancing factor here, 1 is the balancing factor here, and on this side I have 2 is the balancing factor, and here also 2, and here 0. So in this case, I can see that on the left hand side there is unbalance happening. So I'll do right rotation for these three elements. Okay, these three elements I need to do the right rotation. So it will be 6 will be as it is, 3 will go up, and 5 will come down, and on this side 2 will go here, and 8 will be as it is. Now if I write the balancing factor 0, 0, here it will be 0, here it will be 0, and on this side 2 minus 1 is 1. So this is acceptable. Done. I'm done with 2 also. Now I have 4. So in order to add 4, 4 is less than 6. Yes, it will come on the left hand side. 4 is greater than 3. So it will come on this side. And 4 is less than 5. So it will come here. So if I write the balancing factor now, here for 4 it will be 0. For 5 it will be 1. For 2 it is 0 as it is. And for 3 it is 1 minus 2 minus 1. Acceptable. And for 8 it is 0. Now writing for 6. Here I have 1, 2, 3. 3 elements, 3 nodes on the left hand side. And on the right hand side I have 2 elements. So the balancing factor would be 3 minus 1. That is 2. On the right hand side I have 1 element, right? So it will be 2 here. So there is, this part is not balanced, right? So there is imbalance happening at this part. There is imbalance happening at this part. So I need to perform, so firstly it is on left hand side, and again this is on the right hand side. So I need to perform LR rotation. Previously we have discussed for LR rotation, you see the topmost element and the bottommost node, swap those two. So 5 will go up. So when 5 will go up, 3 will come here, and on this side 6 will go. So this part we are done. Now remaining elements, let's add it. Okay, 2 will be here, and 4 will be here, and 8 is greater than 6, so it will be here. So this is what we have obtained after performing LR rotation. Now let me write the balancing factors 0, 0, 0. For this also 0. For this minus 1. For this 2 minus 2 again 0. So it is acceptable. 4 also done. Now I'll move on to 7. So for 7, where should I add 7? 7 is greater than 5. Yes. 7 is greater than 6. Yes. But less than 8. So 7 will come here. Now if I write the balancing factor, for 7 it will be 0, for 8 it will be 1, and for 6 it will be 0 minus 2 minus 2. So this part I can say that it is not balanced. So what rotation will I perform? It is on the right side and here on the left side. So I need to perform RL rotation here. So when I perform, previously we had discussed, in order to perform RL or LR rotation, look at these two elements and swap it. Okay, so 7 will go up. Swap those elements. Swap those elements. Okay, in that case 7 will go here. So I'll write 5, 3, 2, 4 as it is. 7 will go up. Yes. And accordingly 6 will come this side and 8 will come this side. Now writing the balancing factor here 0, 0, 0, 0. Here I get 0, here I get 0. 2 minus 2 again 0. So I can say that finally I have obtained a balanced tree here. Balanced AVL tree is obtained finally. So this was one example. Let's look into the next example now. So here again they have asked us to construct a AVL tree for the list of items. So here I'll start from 21. 21 has balancing factor as 0, minus 1, 0 and 1. So further I can proceed 26. 26 is greater than 21, so I'll write it on the RHS side. So again here balancing factor is 0 and here it will be minus 1. So which is acceptable. Next I have 30. 30 is greater than 26. So I'll write it here. Now if I write the balancing factors, here it will be 0, here it will be -1, and here it will be -2. So I can see that on the on the right hand side there is, it is not balanced. So in this condition I need to perform left rotation. So after performing left rotation, 26 will go up and 21 will come down like this. Okay, so it will be 26, 21 and 30. And by just seeing, we can say that this particular part is balanced, right? Because 0, 0 and 0. Next I have 9. So 9 is less than 26 and 9 is less than 21. So 9 will come here. So if let me write the balancing factors now. So 0 here, 0 here, and 2 minus 1 is 1 here. So it is acceptable. Next I have 4. So 26, 4 is less than 26, 4 is less than 21, 4 is less than 9, and 4 is less than 9. Yeah. So let me write balancing factors now. For 4 it will be 0, for 9 it will be 1, for 21 it will be 2, because 2 minus 0. So I can see that there is it is not balanced in this position. So what will I do? It is on the left side, right? So I'll perform right rotation here. So after performing right rotation, I'll get it as 26 will be as it is, 30 here will be as it is, this 9 will go up, okay, 4 will be here and 21 would be here. Now writing the balancing factors, here I have 0, 0, here also 0, here 2 and here 1. 2 minus 1 is 1. So it is balanced. 4 I am done. Next I have 14. So 14 is less than 26, so it will come on the left side, but 14 is greater than 9, so it will come on the right side here. And for 21, 14 is less than 21, right? So it will come on the left side. Now if I write the balancing factor, for 14 it is 0, for 21 it is 1, and for 9 it is 1 minus 2, minus 1. Okay, done. Now if I write for 26, it is 1, 2, 3. 3 minus 1, 2. So I can see that there is, so this part is not balanced. Here what are the two operations being, what are the two rotations being happening? One is on the left side and the other one is on the right side. So I need to perform LR rotation. For performing LR rotation, we know that I should swap 26 and 21. So 21 will go up, yes, and 9 will come here, and on this side I have 21, and here I have 30, and here I'll have 4, and here I'll have 14. So if I write the balancing factors now, 0, 0, 0, here it is 0, here it is minus 1, here it is 2 minus 2, 0. So 14 I am done. Now I have 28. So 28 is greater than 21, so it will come on this side. Again 28 is greater than 30, 28 is less than 30, so it will come here. Here 0. Now let me write the balancing factors. 0, here I have 1, here I have 2 minus 0. So I'll have, so here I don't have anything here, right? So 0 minus 2, that is minus 2. So I can see that that this part is not balanced. So if I see that I have right rotation happening here, followed by that there is a left rotation also happening. So in this case I should swap 28 and 21. So I will get the AVL tree as 21, 9, 4 and 14. The left subtree will be as it is. Now the right subtree part, 28 will go up, right? 28 will go up, 21 will come here, and 30 would be as it is. So let me write the balancing factor 0, 0, 0, 0. Here again 0, 0. Here 2 minus 2 again 0. So this is the final AVL tree which I have obtained for the given list. So here we have discussed two construction of AVL tree for the given lists. Now let's look into the analysis part. Okay, AVL tree efficiency analysis. So the height of AVL tree with n nodes is bounded by log 2. So this entire so here we have the lower bound and on this side we have the higher bound. Okay, so these bounds imply that the height of AVL tree logarithmically grows with number of nodes, ensuring that the operations are efficient, they remain efficient. So height in best case is log to the base log n. Okay, So height in the best case is log n, in the worst case is this part 1.4405 log n plus 2 minus 1.3277. But in the average case it is 1.01 into log n plus 0.1. Coming to the operations, here on AVL tree we can perform three operations majorly, that is insertion, selection, searching and deletion. So for that, for all three, the complexity here is order of big O of log n. So it goes the same for best case, worst case and average case also. So this was about AVL trees. We discussed what are the rotations, what is the basic understanding of AVL tree. We solved problems also on AVL tree. Let's move on to the next topic now, that is 2-3 trees. So 2-3 trees are a type of height balanced binary search tree. Okay, which was designed to maintain balance by allowing nodes to contain more than one key. So as far as we know, each node can hold only one element, right? Each node can hold only one element, but then here they say that each node can hold more than one element. Okay, so 2-3 tree follows below properties. First property is that it can have a two node structure. That is, if k is the root node, then there could be elements on this side where they are lesser than k value, and on this side there could be elements which are greater than or equal to k value. So this was about the two node structure which we know already. Then here we have the three node structure. Three node structure is somewhat new to us because one node is having two values here, and two values is fine, but here there are three nodes. So one node would be less than the k value. On the right hand side node will have greater than k value, and in the middle it will be both less than and greater than, both in between these two. Okay, so this is the second condition. Third property is all leaf nodes should be at same level. So if I take 1, 2, 3, 4, 5, this is not a 2-3 tree, because if it is still this much, then it can be considered as a 2-3 tree, because all leaf nodes should have same level. Here all leaf nodes are having same level, that is 2. So this was about the basic introduction, the properties which need to be followed in order to construct a 2-3 tree. Now let's look into the procedure to construct a 2-3 tree. So the first procedure is to insert the key into a leaf after going by an appropriate branch. The second step is, so if a node has more than 1 or 2 keys, make sure they are in order. So if it is like 3, 4, 2, then it should be written in the proper order, that is 2, 3, 4. That is one point. If node with 3 keys is a root, split it and create new root with middle element. So this key has 3 nodes in it. This node has 3 keys in it. In this condition, I can write 3 as the middle element, 2 as the left node and 4 as the right node. So this was about the second step. Third step is repeat step 1 and 2 until all keys satisfy the properties. So now let's look into the construction of a 2-3 tree for the given list. So I'll start with 9 being the first element. I'll write 9. So done with 9. Next step is I have 5 here. So I can club 9 and 5. But then it has to be in the proper order, right? So 5 will come first, followed by 9. Next, 5 is done. Next I have 8 here. 8, I can add 8 in this also, because one node can have at least 3 key values. So I can add 5, 8 and 9. Right. So done with 8. Next I have 3. So in order to, so here this step, I need to split 8, 5 and 9 such that 8 becomes the root node and 5 becomes the left subtree, left part, and 9 becomes the right part. So here I can write 5, 8 here, 5 here and 9 here. Next I have 3 here. So 3 will come on this side, right? So I can write 8 here, and here I'll write 3 and 5. And on this side I'll write 9 as it is. Done with 3. Now I have 2 here. 2 again I can add it on this side because it is less than 8. So 8 here, 2, 3 and 5, and on this side 9 will be as it is. Now here again I have one node with 3 keys, so I can shift 8 to the above, and 2 and 5 could be the other elements. So it will be of the form 3 comma 8 will be here, okay, 2 will be here and 5 will be here, along with that 9 will be here. So like we had discussed the condition in the previous page, right? That is, on LHS part here it should be less than the root node. On the RHS side here it is greater than the root node, and in the middle it should comprise within the range of K1 and K2. So that condition is being followed here. Next, I'm done with I have 4 now. So in order to write 4, where will I write 4 now? 4 is between 3 and 8, right? So I'll add 4 here. So it will be 3 comma 8 here, and here 2 as it is. Here I have 4 comma 5, and here I have 9. I'm done with 4. Now I have 7. Where will I add 7? 7 is between 3 and 8, so it will come in the middle. So 3 comma 8 will be here, 2 would be here, 4, 5 and 7 would be here, and on this side I have 9 here. Now if I see 4, 5, 7, I have 5 being the root node, I'll send it on the top. So it will be 3, 5 and 8, and here I'll have 2, 4, 7 and 9. So this again 5 I can send it on the top, right? So it will be of the form 5, 3, 8 here. So when it is 5, 3, 8, 2 and 4 will come this side, 7 and 9 will go this side. So it will be of the form 2 here, 4 here, 7 here and 9 here. So finally I have obtained the 2, 3 tree here. So this was about this question. Let's look into the second question. Construct a 2, 3 tree for the given list. So I'll start from 6. Yes. Then I have 5. So 6 comma 5, or it has to be rewritten as 5 comma 6. Yes. Then I have 1. So it can be written as 1, 5, 6. Done. Then I have 9. So in this case I need to split this, right? So it will be of the form 5 here, 1 here and 9 here. Coming to 6 here. Coming to 9, 9 is greater than 5. So it will come on this side, our right side, right subtree. 1 here and here 6 comma 9. I hope you have understood this step. 9 is greater than 5, no, so it will come on this side, right side. Next I have 7. So it is again greater than 5, right? So it will come on the right side, that is 6, 7 and 9. In this case I will send 7 to the top and I'll keep 6 and 7 here. So it will be of the form 5 comma 7 here, here 1 as it is, here I have 6 and here I have 9. This implies that if the root node is 5 and 7, 1 is less than that, so it will be on the left side. 9 is greater than these two, so it will be on the right side. This is K1, K2. Okay. Then 6 lies between K1 and K2. That is why it is in the middle. Okay. So it is similar to this 3 node structure example. Okay. This. We are done with 7. Next I have 8 here. So 8 comes up, 8 is greater than 7, no. So it will come on the right side. So I have 5 and 7 here. Here I have 1, 6, here 8 comma 9. Next I have 10. So 10 is again greater than 5 and 7. So 5 comma 7, 1, 6, 8, 9 and 10. So when I have 8, 9 and 10, I should send 9 to the top. So it will be of the form 5, 7, 9. Here I have 1, 6, 8 and 10. This I can further write by sending 7 on the top. It will be of the form 7, 5, 9. Here 1, here 6, here 8 and here 10. So this is the 2, 3 tree which was required. So next we'll look into the efficiency of 2, 3 trees. So in the worst case, the height bound is log of n plus 1 minus 1. Because the maximum height occurs when tree has minimum number of nodes for its height. That is, it resembles only two tree structure having only two nodes. Coming to the time complexity, it is order of log n. So operation depends on tree height, leading to logarithmic complexity. Yes. Then in case of best case, height bound would be log cube log to the base 3 n plus 1 minus 1. This is because the minimum height occurs when tree has maximum number of nodes for its height. That is resembling only 3 tree structure. That is each node would have 3 values like that. Okay. Each node would have 3 subnodes, this kind of configuration. Coming to the time complexity, it is same as the worst case, order of big O of log n. Coming to average case, it lies between the worst and best, and time complexity is also the same, big O of log n. So this was about 2-3 tree. I hope you have understood the balanced search trees. If you have any doubts, do let me know in the comments and subscribe to my channel. Thank you.